All right, welcome to our third video for this week. We are talking about square roots and square root functions. We also call them radicals. Radical is the symbol, the square root symbol. What you need to remember is that C is square root if C of A if C squared equals A. For example, 16 has -4 and 4 as square roots because -4 times -4 is 16 and 4 times 4 is 16. However, -9 does not have a real number square root because what times what is -9, where it's the same thing, nothing. Now we'll talk about how to handle that later, but you can see that there is a difference. We can get a real number if we take a square root of a positive number, but we won't get a real number if we take the square root of a negative. So if you wanted to find the two square roots of 49, we would get 7 and -7. However, if you see the square root symbol, we want the square root, meaning we want the positive square root. It's called the principal square root. So if you just see square root of 81, we would say 9. Okay, and so on. So I have lots of examples. They're all in doc sharing. Oh, I did want to show you parts of a radical. Okay, you can see that I have the word written here, radicand. That's the part on the inside. Okay, all of that, what I just highlighted, those are radicands. The index, I don't have that written here, but the index is the little number out here in the crook. Okay, these are all 2's, index of 2 in each case, because there's no index written at all. So if you don't see an index written at all, it is understood to be 2 or the square root. But if a cubed root is meant, you'll see in 3 an actual number. Okay, so the square root of 8 squared is 8, and the square root of -8 squared is 8. However, it is not -8. Okay, so we don't just blindly take what's inside the radical and write that down. Okay, and that's because -8 squared is 64, and the square root of that, of course, is 8. So if we're taking the square root of something and we're talking about a variable, we need to have absolute value bars around the variable. Those are the two lines you see surrounding that A. Okay, right here. Oops. Right here and here, those are your absolute value bars. And if you look at your keyboard, if you look at the enter key, it's right above that. You would just hit shift to get that. And you'll use it when we want to show that the answer is positive. Okay, here's some of the rationale. -2 to the first is -2. -2 to the second is +4. -2 to the third is -8, and so on. If we look at 2 to the first, 2 to the second, 2 to the third, those are always going to be positives. Okay, so anything raised to an even power has to be positive no matter what the original number is. But since that original number could be positive or negative if we're talking about a variable, we need those absolute value bars. Okay, so even if we have, and you see this example at the bottom, the square root of x to the 10th, all right, we know that's x to the 5th, but I have to put the absolute value bars because x to the 5th, as you see above, could be positive or negative, and we just want positive values. I do want to caution you about one thing. The cubed root of something can be negative, so don't necessarily think there's a problem if you're taking the cube root of a negative. Let me show you a really quick little example. Let's say I have, let me get my pen here, the cubed root of -8. All right. In other words, what times what is -8? And the answer is -2. And that's fine being negative. As a matter of fact, it has to be negative because we wouldn't get -8 otherwise. So it just depends. Okay. If you have a even root, you will need the absolute value bars if you have a variable. Okay. And you see it here in example A. Okay. I think we've talked about example C already. Okay, example B, I don't need the absolute value bars because I come up with an answer of m to the 6th. No matter what m is, raising it to an even power makes it positive anyway, so we're good. All right, cubed roots I talked about a little bit. It would look like that. And here's an example. So the cubed root of negative 27x to the third, think about groups of 3. So what times what times what is negative 27? The answer is negative 3. What times what times what is x to the third? The answer is x. And that's why negative 3x is the answer. Okay. Kind of talked about that a little bit. Here are some more examples. And this is in the PowerPoint presentation, so I think I will leave it. But look at example C. Not a coincidence. All right. And just a little discussion here about how to simplify radicals. Remember, I'm not calling them square roots now because I'm not looking at a square root. In this case, I'm looking at fourth roots. So the fourth root of 81 is what times what times what times what is 81. Okay. But on example C, I need to have those absolute value bars around the variable. You could put it around the whole thing if you wanted to. That's all right. But definitely around the variable because m could represent a negative number, and being a fourth root, I don't want that. The slide I just passed is a little confusing for some. People have told me before that that didn't help them a lot, but it just is a little, you can look at it in the PowerPoint presentation and see if that's something that would be helpful to you with when to and when not to use absolute value bars. I think your logic will carry you through fine on that. And the thing to remember here is that exponents can be fractions, and the great news is there's no new rules. So a to the 1/2 times a to the 1/2, we've already talked about in our first video for this week. If you have the same base raised to some power, what do? You add, right? A half plus a half is 1, the end. Okay. And I want to show you this. If you have something raised to the 1/2, as an example, that means the square root. Okay, so the n ends up being the index. The exponent ends up being the exponent right there. So if I had 5 raised to the 1/2 power, okay, that is the same thing as the square root. I don't need to write that little 2 in the index, but that's where it is, of 5 to the first. In this case, I don't need the little first power because it's implied. Okay, here's some more examples about how I can go from one form to the other. It just takes a little practice. It probably looks weird at first, but it just takes a little bit of practice. And more examples. Okay, and that's actually what I just showed you a second ago. So, for example, 8 to the 2/3 is kind of confusing right now, but that means the third root of 8 to the 2nd. And I know that the third root of 8 is 2. So this simplifies 2 to the 2nd, or 4. So you can see, you know, I don't think looking at 8 to the 2/3 immediately makes me think, oh, 4. But you can see that rewriting it in radical form gets us there. Okay, same with example B. 9 to the 3/2 just means the square root of 9 to the 3rd. Square root of 9 is 3, so we have 3 to the 3rd, or 27. So I have more examples for you. All right, negative rational exponents. Nothing's changed. So I'm going to go through this kind of quickly too because nothing's changed. That still means flip it. Okay, so I think I went back a little too quickly there. Coming back to that, a to the negative some fraction just means 1 over a to the positive fraction. Okay. And just remember, raising something to a negative exponent, a negative power, does not mean the whole term is negative. I mean, if it is, it is, but that negative exponent doesn't make it negative. So don't make that mistake. All right, so 8 to the negative 2/3 just means 1 over 8 to the positive 2/3, and we've already talked about 8 to the 2/3 simplifying to 4. So all this shows is the exact same thing we've already talked about in the first video, that even if you have fractional exponents, all of the same laws apply. So I'm going to leave these examples for you for the PowerPoint presentation. If you'll download that and take a look at it, it's going to be there. You can see, I mean, I'm flipping through it quickly here. Don't panic. There's a ton of these waiting for you over in doc sharing. Okay. Don't make this mistake. Okay, if you have the nth root of something times the mth root of something, you can't combine those. So don't do that. All right, I do want to show you this. You can simplify by factoring. And the square root of 300 is 100 times 3, and it's a lot of things. There's a lot of things that we can multiply together to get 300, 60 times 5, and so on. But 100 times 3 is appealing because I can take the square root of 100, and when I do, I get 10. That comes outside of that radical. I can't take the square root of 3, which is what's remaining in there, so it stays under the radical. Now I'm going to show you something I do that you might find helpful, because you might not always be able to look at something. It might even be more complicated than 300. It's not easy always to look at something and simplify it. So I take the number and start dividing by the smallest prime number that'll go into it. And don't worry, because it looks like it's going to take forever and it doesn't. I'm going to keep dividing by the smallest prime number, okay, which is again 2. Now 2 won't go into 75, but 3 will, my next prime number. That's a 3, 25. And 3 won't go into that anymore, but my next prime number will. And then I'm done, because anything else would give me a 1. 1 isn't prime. So I'm going to change pen colors here and just show you how I do this, because I do it in a very visual way. I'm looking at, since I'm taking the square root, I'm looking at pairs. If I was taking the cubed root, I'd be looking at groups of 3. Like pairs, that's a little 5 there. It didn't really show up very well, but there's a pair. I've got a 2 and I've got a 5. So I'm going to multiply 1 from each group and I get 10. All right. What didn't get circled stays inside the radical, and that's my final answer. So hopefully that makes sense. And you can definitely use that method if you'd like. More examples. And more examples with multiplying and simplifying. Remember, you can multiply anything, but you can't add or subtract anything. So we can multiply anything, but not add or subtract anything. So tuck that in the back of your mind. In our next video, we're going to talk about imaginary and complex